This conference will now be recorded.
Good afternoon all. Today I'm going to give a demo on design for testability, which is DFT. Before we go into what is DFT, we'll first try to understand what is VLSI design. VLSI stands for Very Large Scale Integration. Okay? So it means implementation of million transistors in a small area. Okay, implementation of million transistors in a small area. So goal of VLSI, if a particular company is designing a chip, then they will be having some primary conditions or primary targets that has to be met. That is what is the goal of VLSI. So first one is high performance. Second one is like low power. So we go for low power design in order to achieve longer battery life, and then low area. So if in case our chip size is huge, then our product size will be huge. So that's why we try to go for low area design. And this is how our chip looks like after manufacturing. Okay. And next we'll try to understand what is ASIC. ASIC stands for Application Specific Integrated Circuit, which means the IC integrated circuit which we are designing, it will be specific to a particular application. For example, if we are designing a modem chip, it cannot be used as a chip which is responsible for deployment of airbag in the automobile. Okay, so a modem chip, it will not be used. It cannot be used as a chip which is responsible for deployment of airbag in your automobile. So that is what is called as application specific integrated circuit. The IC which we are designing, it will be specific to a particular application. So ASIC flow means it actually gives the steps which we need to follow for designing a chip. Okay, ASIC flow means it gives the steps which we need to follow for designing a chip. So if it actually involves the various steps which is involved in the process of chip design. So the first one is the design specification stage. So design specification stage means based on the application for which we are designing a chip, certain specifications will be decided, like what has to be the speed, how many memory modules are required, how many processors are required, how many sensors will be required, what has to be the power. So such kind of specifications will be decided. So that is what is the design specification stage. So based on the application for which we are designing the chip. Based on the application for which we are designing the chip. So certain specifications will be decided, like what has to be the speed, how many memory modules are required, how many memory modules, how many memory modules, and then uh, processors, and then sensors are required, and what has to be the power. So such kind of specifications will be decided in the design specification stage. Okay, based on the application for which we are designing the chip. Certain specifications like what has to be the speed, how many memory modules, processors, sensors are required, what has to be the power. So those kind of things will be decided. And then we have the design code stage. So in design code stage, what will happen is the design code of the chip will be written. It will be done by the design team. So they will be describing the functionality of the chip. Okay, they write the design code of the chip. So basically the design code, it will be written in behavioral model or data flow level model. So it will be in behavioral model or data flow level model. And then we have the verification. So verification, they actually validate the functionality of a design to ensure that it meets the required specification and performs as intended. Okay, so that is what is a verification team. So they will validate the Validate the functionality of a design. Functionality of a design to ensure that it meets the required specification and performs as intended. It meets the required specifications and performs as intended. So this is the role of the verification. And then we have the synthesis team. So during synthesis, what will happen is the behavioral or data flow level model code is there, right? So that will be converted into a structural form, or we can call it as a technology node specific gate level netlist. So this behavioral model or data flow level model code will be converted into structural form. Will be converted into structural form, or we can call it as technology node specific gate level netlist. And next we have the design for test team. So design for testability or DFT team, we will be inserting our own test structures into the design, like scan insertion, MBIST insertion, boundary scan insertion. Like that, we will be inserting our own test structures into the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. We'll try to understand about this design for testability team in detail during the next slides. And then we have the physical design team. So physical design team, they convert the gate level design into a layout form. Physical design team, they convert the gate level design into layout form. Gate level design into layout form. Okay. And then we have the sign off. So in sign off, like we have these things like static timing analysis, STA, physical verification, PV, and logical equivalence check, LEC. Okay. So we have these three things. One is STA, static timing analysis, PV is physical verification, and LEC is logical equivalence check. So static timing analysis, STA, as its name suggests, it is a method of validating the timing performance of a design by checking all possible paths for timing violations. That is what is STA. It is a method of validating the timing performance of a design by checking all possible paths for timing violations. So that is what is static timing analysis, STA. And then we have the physical verification, PV. So physical verification, PV, it is actually to verify the layout of the circuit. Physical verification is to verify the layout of the circuit. And then we have LEC, logical equivalence check. Logical equivalence check is actually done in order to check whether the final design is logically equivalent to the original design or not. Okay, so LEC is done to check if the final design is logically equivalent to the original design or not. So why? Because if you see in the process of chip design, why LEC is performed is, if you see in the process of chip design, our design undergoes a lot of changes. So if you see, first we had started with the design code stage where the behavioral and data flow level model code is written, and then during synthesis it will be converted to a structural form or technology node specific gate level netlist. And if you are going for low power design, then certain special cells like clock gating cell, retention registers, so isolation cells, so those kind of cells also will be added into our design. And at the time of DFT, we will be adding our own test structures into the design, like scan insertion, MBIST insertion, boundary scan insertion, like that we'll be adding our own test structures into the design. So if you see in the process of chip design, our design is undergoing a lot of changes in each and every stage. So that's why LEC is done to check whether the final design is logically equivalent to the original design or not. So actually LEC will be done after each stage, like after synthesis, after DFT, after PD, like the DFT, like that LEC will be done after each stage. Okay. And then tape out. So tape out means it is like delivering the database to the manufacturing unit is called as tape out. Delivering the database to the manufacturing unit. Okay, delivering the database to the manufacturing unit is called as tape out. And then we have packaging and testing. So packaging and testing, it is actually done after manufacture. Packaging and testing will be done after manufacture. So after manufacturing, here if you see this big circle will be the wafer and each individual portion is the die. So packaging means covering this die with a protective layer is called as packaging, and testing is actually done to check whether our chip is good or not, or whether that is whether our chip has any manufacturing defects or not. So this is what is the complete ASIC flow, the various steps which is involved in the process of chip design. So in our upcoming slides, we will try to understand more in detail about this design for testability as well as this testing. Okay, we'll try to understand more in detail about the design for testing and then this testing. Okay, so what is DFT? So DFT is actually to insert test structures into the design. Like we will be adding our own test structures into the design, like scan insertion, embed insertion, boundary scan insertion. Like that, we will be adding our own test structures in the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. Okay, pre-silicon stage means it is before manufacturing. Okay, so to facilitate. Okay, to facilitate. To facilitate means to help. Facilitate means to help in the detection of manufacturing defects in the chip. So DFT is to insert test structures in the design. We'll be adding our own test structures like scan insertion, embed insertion, boundary scan insertion. Like that, we'll be adding our own test structures into the design during the pre-silicon stage. Pre-silicon stage means before manufacturing. To facilitate, which means to help in the detection of manufacturing defects in the chip. So, if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. Okay, so that is what it means. If suppose a particular chip fails after manufacturing, particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. What manufacturing defect has caused the chip to fail. So if suppose a particular chip fails after manufacturing, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. And then role of DFT engineers. So role of DFT engineers, so DFT is to insert test structures in the design during the pre-silicon stage to facilitate the detection of manufacturing defects in the chip. Yes, correct. So that is what we had seen it in the previous slide. And then DFT engineers do not check the functionality of the chip. They rather check the quality of the chip. DFT engineers do not check the functionality of the chip, we rather check the quality of the chip. So let's try to understand this point. Just a second. This has to come here. So let's try to understand this point. So say for example you have a half adder. So for a half adder, what is the expression for sum? Sum will be A XOR with B, carry will be A. Whether this is correct or not, whatever is written here, whether this is correct or not, that is what will be checked by the functional verification team. Because someone by mistake, if they have written sum is equal to A plus B, carry is equal to AB. If someone mistakenly they have written sum is equal to A plus B, carry is equal to AB, then this will not function like a half adder. This will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. Okay. So like for a half adder means sum should be A XOR with B, carry is equal to AB. So whatever is written, whether it is correct or not. So by mistake, if someone has written sum is equal to A plus B, carry is equal to AB, this will not function like a half adder. So this is what will be checked by the functional verification team. They will be checking the functionality. DFT engineers, we do not check the functionality. Okay, DFT engineers, we do not check the functionality. We check whether each and every net of this half adder is free of defects or not. So for example, this is our intended design. So A XOR with B. So A and B, it is coming from some flops and output is going back to some flop. And A and B, it is coming from carry and then output is going. A and B, it is coming from some flop and then the output of this flop is sorry, A and B, it is coming from some flop. So both are ANDed. So that is what is carry and that is going to a flop. Okay, so this is what is our intended design for a half adder. Now suppose during manufacturing, A net of this AND gate unintentionally it got connected to ground. Unintentionally during manufacturing, A net of this AND gate has got connected to ground. Okay, so these kind of things is what will be checked by the DFT engineers. So DFT engineers, we do not check the functionality. We check whether each and every net of this half adder in this example is free of defects or not. So this is our intended design. A and B, it is XOR and it is nothing but sum. A and B, it is ANDed and that is nothing but carry. A and B, it is coming from some flops. Sum and carry, it is going back again to some flops. So this is the intended design. Okay. So suppose during manufacturing, A net of this AND gate unintentionally got connected to ground. Okay. So these kind of things is what will be checked by the DFT engineers. So DFT engineers do not check the functionality. We check whether each and every net of this half adder in this case is free of defects or not. Okay. So this is what is the role of DFT engineers. So DFT engineers, we do not check the functionality of the chip. We rather check the quality of the chip. And in our main course, we will also explain, we will explain it in detail about the differences between functional verification team and DFT team. So this is a demo session, so we have just given an overview about it. In the main training, you'll be able to understand what is the difference between a DFT engineer and a functional verification engineer more in detail. And we'll also try to understand why do we need both DFT team as well as functional verification team. Okay, why do we need both DFT team as well as the verification team, functional verification team? Why do we need both of them? So we will try to understand it in detail during the regular course. Okay, so we'll try to understand in detail what is the difference between DFT engineer and a functional verification engineer. More in detail, we'll try to understand. And why do we need both DFT team as well as functional verification team? We'll try to understand it. Okay. Now this testing. So in the ASIC flow slide, we had seen a process called as testing, right? A step called as testing. So it was actually done after manufacturing. So testing is actually a process of determining whether a device is good or not. So whether our chip is good or not, whether there are any manufacturing defects in our chip. So that is what is testing. Testing is a process of determining whether a device is good or not. Okay. Testing includes test pattern generation, application, and output evaluation. Testing includes test pattern generation, application, and output evaluation. So these test patterns are there, right? So these test patterns, it will be generated by the DFT engineer before manufacturing itself will generate the test patterns. So it will be consisting of the input sequence and expected output. Okay, it will be consisting of input sequence and expected output. Okay. So now what will happen is this input sequence, it will be applied onto the chip. This input sequence will be applied onto the chip, and then the output of the chip will be compared with the expected output. Output of the chip will be compared with the expected output. Okay. So now if the output of the chip, if it is equal to the expected output, it means that the chip is good. Okay, which means there are no manufacturing defects in the chip. Output of the chip, if it is not equal to the expected output, it means that the chip has failed, which means there are some manufacturing defects in the chip. Okay, so these test patterns are used, right? These test patterns, it will be generated by the DFT engineer before manufacturing itself. It will be consisting of input sequence and expected output. So the input sequence will be applied onto this chip, and then the output of the chip will be compared with the expected output. Now the output of the chip, if it is equal to the expected output, it means that the chip is good. So which means that there are no manufacturing defects in the chip. Output of the chip, if it is not equal to the expected output, it means that the chip has failed. There are some manufacturing defects in the chip. So if a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. If a particular chip fails, DFT engineers will be able to tell what manufacturing defect has caused the chip to fail. And possible outcomes of testing. So there are basically 4 possible outcomes of testing. So if a good IC, if it passes the test, it is called as true pass. Good IC, if it passes the test, it is called as true pass. Okay. And then if a defective IC, it has to fail the test. Defective IC means it should fail the test. So defective IC, if it fails the test, means it is true reject. Now, if suppose a defective IC, if it passes the test, if it passes the test, it is called as test escape. It is also called as under testing. And if a good IC, if it fails the test, it is called as yield loss. It is also called as over testing. And goal of good testing is actually to reduce the test escape and yield loss. So what is yield? Yield means number of good chips by total number of chips. Out of a total number of chips that has been manufactured, how many chips are good? So that is what is called as yield. Number of good chips by total number of chips. So goal of good testing is actually to reduce the test escape and yield loss. And manufacturing defect. So what are manufacturing defects? Manufacturing defects are the defects that are caused due to process variations and random imperfections. So process variations means slight variation in transistor channel length, metal interconnect width and thickness. All those things can actually result in logical and timing variations. Okay. And random imperfections means unintentional shorts, unintentional opens. So that is what is called as random imperfections. Okay. So and what is the flow of DFT? So flow of DFT means, so first we have the insertion phase. So during the insertion phase, we will be inserting our own test structures into the design, like scan insertion, MBIST insertion, boundary scan insertion, like that. We will be adding our own test structures into the design. And then we have the generation. So we'll be generating the patterns, so that those patterns, it will be consisting of the input data and then the expected output. And then validation is actually done using simulations. So we'll try to understand what is simulation in the upcoming slides. A brief idea on what is called as simulation in the upcoming slides. Okay. So now we'll just try to understand what are all the topics will be covered as a part of our DFT course. So first is scan insertion. Okay, so the first topic which we'll be covering is scan insertion, then scan compression, and then on-chip clock controller, automatic test pattern generation, simulations, JTAG, joint test action group, MBIST, memory built-in self-test, and boundary scan. So these are all the topics which will be covered in our course. Okay, these are all the topics which will be covered in our course. So now we'll just try to see an overview on these topics, and we'll just try to see what all the subtopics will be covered here in our course. So the first one is scan insertion. So scan insertion means what will happen. So all the normal flops in the design, it will be converted to a scan flops. And these scan flops will be stitched into scan chain. This is what is scan insertion. All the normal flops in the design will be converted to scan flops, and these scan flops will be stitched into a scan chain. So, in our course, we'll just try to understand in detail, like what is the functionality of a scan flop, what is the functionality of a scan chain, all those things we'll try to understand it during our regular course. So basically, scan insertion means all the normal flops in the design, it will be converted to scan flops, and these scan flops, they are stitched into a scan chain. And why do we need to do that? Why do we need to convert all the normal flops into scan flops? And why do we need to stitch the scan flops into a scan chain? So we need to do this in order to gain controllability and observability of the design. In order to gain controllability and observability of the design. Which means in order to easily control and observe our design, we will be going for scan insertion. We'll just try to have an overview about it. What does easily able to control and observe our circuit? That is, in order to gain controllability and observability of the design. So, what does that mean? We'll just try to understand it with the help of a small example now. Okay. We will once again take up this example when we do the main course. We'll once again take up this example and we'll try to analyze it in more detail. As of now, I'm just giving you an idea about it. So say for example, I am having a design. So in my design, I have a 10-bit counter, I have a counter initialization and a counter observation circuit. So suppose if the counter is failing, that is after counting 999, instead of counting 1000, it again counts 999. Okay, so suppose if the counter is failing, after counting 999, instead of counting 1000, it is again counting 999. We'll just try to see how many clock pulses will be required by the functional verification team and how many clock pulses will be required by the DFT team in order to find out that the counter is failing. In order to find out that the counter is failing. Okay. So functional verification team, they require more than 1000 clock pulses to detect that the counter is failing. Functional verification team, they require more than 1000 clock pulses to detect that the counter is failing. So why we are telling like that, we'll try to understand it. Okay. So like functional verification team, as you know, they will be checking the functionality. Functional verification team, they check the functionality. Check the functionality. So check the functionality in the sense, like in this case, they check whether the counter properly counts from 0 to 1023. It's a 10-bit counter, right? So that's why they will check whether the counter properly counts from 0 to 1023. Okay. So check whether the counter properly counts from 0 to 1023. Okay, so they check whether the counter properly counts from 0 to 1023. So functional verification team, they check the functionality. So in this case, what is happening? Counter is actually failing at the 1000th pulse, because as we saw in the previous slide, at the 1000th pulse only, so like instead of counting 1000, it is once again counting 999. Okay, after counting 999, instead of counting 1000, okay, instead of counting 1000, it again counts 999. Okay, so that's why what is happening? Okay, counter is failing at the 1000th pulse. Counter is failing at the 1000th pulse. Okay, so that is why 1000 pulses are required for this. 1000 pulses are required for this. Okay, and then some more clock pulses will be required for counter initialization and counter observation. Okay, some more clock pulses will be required for counter initialization and counter observation. So counter initialization means like uh, the counter, it has to be brought to some initial state, and counter observation means the output of the counter, it has to be taken to some register and the register has to be read. So some more clock pulses will be required for counter initialization and counter observation. So some more clock pulses will be required for counter initialization and counter observation. So all the above, we can say that functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Okay, because functional verification team, they check the functionality, that is they check whether the counter properly counts from 0 to 1023. So in this case, counter is failing at the 1000th pulse, so 1000 pulses will be required for this, because at the 1000th pulse only, instead of counting 1000, it is once again counting 999. Okay, so that's why counter is failing at the 1000th pulse, so 1000 pulses are required for this, and some more clock pulses will be required for counter initialization and counter observation. So counter, it has to be taken to some has to be brought to some initial state, and then the output of the counter, it has to be taken to some register and the register has to be read. Okay, so that is what is called as counter initialization and counter observation. So some more clock pulses will be required for counter initialization and counter observation. So ultimately, we can say that functional verification team, they require more than 1000 clock pulses to tell that the counter is failing. Whereas DFT team, we will be able to tell that the counter is failing approximately in the range of 100 clock pulses. Range of 100 clock pulses means it can be somewhere like 80 or 90 or 100, 120, etc. That is what is called as range. That is what I meant by range of 100 clock pulses. So DFT team, we will be able to tell that the count is failing approximately in the range of 100 clock pulses, like 80, 90, 100, 120, like that. In the range of 100 clock pulses itself, we'll be able to tell that the counter is failing. Functional verification team, they required more than 1000 clock pulses, whereas DFT team, we require approximately in the range of 100 clock pulses to tell that the counter is failing. So how DFT team, we are able to tell that the counter is failing in such like if you see in significantly less number of clock cycles as compared to the functional verification. You can observe DFT team, we are able to tell that the counter is failing in significantly less number of clock cycles as compared to the functional verification team. Okay, so how it is like that? It is because DFT team, we go for scan insertion. Okay, DFT team, we will be going for scan insertion. Because of this, we are easily able to control and observe our circuit. We'll try to understand it about this point in detail during our course, and this explanation also, how DFT engineers are able to tell that the count is failing in approximately the range of 100 clock pulses itself, how we are able to do that. Okay, you'll be able to, for in order to understand this point, you first need to understand what is a scan cell, how it operates, and then what is a scan chain, how it operates. All those things you need to understand. So that's why we will once again take up this example in the main course. While doing the main course, we will once again take up this example and we will discuss more in detail. Okay, like after completing, like what is scan chain, what is scan cell, all those things after completing, we will understand like how DFT engineers are able to tell that the count is failing in approximately in the range of 100 clock pulses itself. How it is like that, we'll try to understand, and we'll also understand more in detail we will also take this example and understand more in detail about these things. And when we do this example in the main course, at that time you will have a clarity on what is the difference between functional verification team and the DFT team, and why we need both the functional verification team and DFT team. So we will once again take up this example during our main course and understand it. At that time, you'll be getting a clarity on all these points clearly. Okay. So what is the difference between functional verification team and DFT team, and why do we need both functional verification team and DFT team? So when we do this example more in detail during our main course, you will be able to understand it in detail. You'll get the clarity of it. And DFT team will also be able to tell. DFT team will also be able to tell what manufacturing defect has caused the chip to fail. Okay, DFT team will also be able to tell what manufacturing defect has caused the chip, or in this case, the counter. Okay, DFT team will also be able to tell what manufacturing defect has caused the counter to fail. Okay, so yeah. So this also, how DFT team are able to tell what manufacturing defect has caused the counter to fail. How it is like that. That also when we do the regular course, you'll be able to understand. Okay, you'll be able to understand when we do the regular course. Okay, so at the end of the 3.5 months to 4 months course, the DFT advanced course when you complete it, at that time you'll be getting a clarity on how DFT engineers are able to tell what manufacturing defect has caused the counter to fail. So now, as a part of scan insertion topic, we'll just see what are all the things will be, what are all the subtopics will be covered as a part of the scan insertion topic. So like topic 1 is scan insertion. So now currently I'm just telling about the theory part. So practicals, what are all the things will be covered, I will cover it later. Okay, so topic 1 is scan insertion. I'll just tell you what are all the subtopics will be covered as a part of this training. And as of now, I'm telling only about the theory portion. Later, we will discuss about the lab part. Okay. So in scan insertion, like in day 1, we will complete what is a scan cell. Okay, what is a scan cell, and then what is a scan chain, what is a scan chain, and then like how a scan chain operates. Okay, how a scan chain operates, scan chain operation. So these things we'll try to understand it in the first day. And then in the second day. And then in the second day, so like we'll try to understand what is the need of scan insertion. What is the need of scan insertion? So that is what, in order to gain controllability and observability of the design. So that is what is the need of scan insertion, right? We'll try to understand it. So during this time only we will understand whatever counter example we saw, right? We will try to take that example once again, and we will try to understand it in detail. We'll try to explore the counter example in detail during this part of the training. And at the end of this topic, when we complete this topic, and when we do the need of scan insertion topic, that is when we discuss about the counter example which we saw in the previous 2 slides, when we discuss about it in detail. So at the end of the topic, you will be able to understand what is the need of scan insertion, and along with that, you will also be able to understand what is the uh, what is DFT engineer, what is the difference between DFT engineer and functional verification engineer. Okay, and functional verification engineer. And then you will also be able to understand why do we need both the DFT engineer as well as a functional verification engineer. Why both DFT engineer and as well as functional verification engineer are required. As well as functional verification engineers are required. So all these things you will be able to understand when we complete this topic. Okay, so during this topic only, we'll be taking the counter example once again. Whatever counter example is we'll be taking that topic and we'll discuss more in detail about it. So when we explore that counter example in detail during our main course, so at the end of that you'll be able to understand what is the need of scan insertion, what is the difference between the DFT engineer and the functional verification engineer, and why do we need both the DFT engineer as well as a functional verification engineer. And then in day 3 we will try to understand the various scan DRCs. So DRC stands for design rule checks. DRC stands for design rule checks. Okay. So DRC's full form is design rule checks. So which means, okay, so what is scan insertion? Scan insertion means a normal flop, it will be converted to a scan flop, and these scan flops will be stitched into a scan sheet. That is what is the definition of scan insertion we had seen, right? Now, if a normal flop, if it has to be converted to a scan flop, then it has to pass certain rules. It has to pass certain rules. So those rules are only called as these DRCs, design rule checks. Okay. So what is the definition of scan insertion? Definition of scan insertion is all the normal flops, it has to be converted to a scan flop, and the scan flops will be stitched into scan sheet. If a normal flop, if it has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as the DRCs. Okay. So there will be various DRCs in scan insertion, like we'll be discussing about clock controllability DRC. Okay. So we'll be discussing about clock controllability DRC, and then set reset controllability DRC, set reset controllability DRC, and then we'll be discussing about feedback loop DRC, and then we'll be discussing about the X source DRC, then we'll be discussing about the bus contention violation, and then we'll be discussing about the potential raise DRC, okay. So these are all the various DRCs which we will be discussing it on day 3. And then in day 4 we'll take a new topic called as balancing of scan chains. In day 4 we'll take a new topic called as balancing of scan chains. Balancing means keeping almost equal number of flops in all the scan chains. So that is what is called as balancing. Balancing means keeping almost equal number of flops in all the scan chains. Keeping almost equal number of flops. Almost equal number of flops in all the scan chains. That is what is called as balancing. Balancing means keeping almost equal number of flops in all the scan chains. And why do we need to go for balancing? So why do we need to go for balancing is we go for balancing in order to reduce the test time. Okay, we go for balancing to reduce the test time. To reduce the test time. Okay, and how it happens? How if you go for scan chain balancing, you are able to achieve reduction in test time? How it is like that? We will discuss during our course. We will discuss it during the course. Okay. And then, if you want to achieve balancing, then we need to go for certain techniques like edge mixing and domain mixing. Okay, so balancing of scan chain means keeping almost equal number of flops in all the scan chains. And why do we need to go for balancing? To reduce the test time, and how we are able to do it. How if you go for balancing, we are able to achieve reduction in test time. We will discuss it during the course. And in order to achieve balancing, we need to adopt certain techniques like edge mixing and domain mixing. Okay, so like in order to achieve balancing, achieve balancing, okay, we need to go for edge mixing and domain mixing. We need to go for edge mixing and domain mixing. So what is edge mixing, what is domain mixing, all those things we'll try to understand it. Okay, in day 4. In day 4, all those points we'll try to understand. Okay, in day 4, we'll first try to understand like what is balancing. Balancing means keeping almost equal number of flops in all the sketching. And we go for balancing to achieve reduction in test time. How we are able to achieve reduction in test time if we go for balancing, you'll be able to understand it when we do this topic. And in order to achieve balancing, we need to go for edge mixing and domain mixing. So what is edge mixing? What is domain mixing? And how if you go for edge mixing and domain mixing, you are able to achieve balanced scan chains. All these points you will be able to understand when we do this topic on day 4. Okay. And then next, in day 5, what we will discuss is, so if you go for edge mixing and domain mixing, you go for edge mixing and domain mixing, then it will in turn introduce some more problems. To go for edge mixing and domain mixing, it will in turn introduce some more problems. So that is what is called as problems in edge mixing and domain mixing. So we'll try to understand on day 5, we'll try to understand what are all the problems edge mixing and domain mixing will cause and how to resolve them. Okay, we'll understand what are the problems we will face during edge mixing and domain mixing, and we'll see how to resolve them. Okay? Problems in edge mixing and domain mixing and how to resolve them. Edge mixing and domain mixing. Okay, problems in edge mixing and domain mixing and how to resolve them. These are all the major topics which we will be discussing for scan insertion. And on day 6, we will discuss some more like definition type topics. So, some small definition type topics we'll try to understand it on day 6. Okay, these are the major topics which we'll be discussing, and on day 6, we'll try to understand some small definition type topics like types of scan cells. Like that, we just try to see some small theoretical definition type topics. We just try to see it. Okay, so this was regarding scan insertion. Next is scan compression. So scan compression means a scan channel is internally divided into multiple scan chains. That is what is called as scan compression. A scan channel is internally divided into multiple scan chains, or you can even say that the multiple scan chains will be compressed into a channel. So these multiple scan chains, that is what we call it as the internal chains. Okay, so these multiple scan chains will be calling it as the internal chains. These are the internal chains. So these internal chains, they will be compressed into external channels. These internal chains will be compressed into external channels. That is what is called as scan compression. Internal chains will be compressed into external channel. So this is nothing but your external channel. This is external channel in, this is external channel out. So these internal chains will be compressed into external channels. You can see it in this way, or else however it is written. So this external channel, it is internally divided into multiple chains. Both the ways are correct. Okay, internal chains are compressed into external channels is also correct, or else external channel is internally divided into multiple scan chains. So both are the definitions of scan compression. Okay, so the internal scan chains will be compressed into external channels. So that is what is called as scan compression. Okay, and why do we need to go for scan compression? We need to go for scan compression in order to reduce test time and also to reduce the test data volume. We need to go for scan compression to reduce the test time and to reduce the test data volume. Test data volume is nothing but the number of bits of patterns. Okay, test data volume is nothing but the number of bits of patterns. Okay. And how if you go for scan compression, you are able to achieve reduction in test time and you are able to achieve reduction in test data volume, you will be able to understand when we do the course. So when we do the course, we will logically also explain. We will logically explain this, and we will also explain with the help of formula. We will take the formula of test time and test data volume. We will substitute the formula. We will substitute the value in the formula, and we'll try to see with the compression and without compression. We will compare the results. Okay. So during our course, we'll try to understand how if you go for scan compression, you are able to achieve reduction in test time and reduction in test data volume. So this will be covered during our course. Okay. So both logically as well as with the help of formulas, we will cover it in our course. Logically, logically also will show. We'll also show with the help of some formula. Yes, with some formula. With formula. Okay. And then if you want to achieve scan compression, then if you are using mentor graphics descent tools, if you are using a lot, you need to add up a logic. So that logic is nothing but the EDT logic, embedded deterministic test. Okay, embedded deterministic test. Embedded deterministic test. So which is nothing but EDT. If you want to achieve scan compression, if you are using mentor graphics tools, you need to add up a logic which is embedded deterministic test, EDT logic. Okay. So this is how a EDT logic will look like. I have just kept only two components, decompressor and then the compressor component alone I have kept here. Apart from that, you will also be having the controller logic and then the bypass logic. All these things will be there. So we will discuss it in detail. So when we do this course, we will try to understand about each of these component of the EDT logic. Okay, each component of this EDT logic. Okay, so like what is it? The decompressor component, and then the compressor component, and then the controller component, and then the bypass component. Okay, so about all these things we'll try to discuss it. Okay, so when we do the scan compression, so in order to achieve scan compression, if you are using vector graphics tools, you will be adding a logic called as EDT, embedded deterministic test. So there are four components inside the EDT logic. You have four components, which is decompressor, compressor or compactor logic, controller, and then bypass. We will understand the structure and functionality of each of these components when we do the regular course. Okay, so these are all the topics which will be covered as a part of scan compression training. Okay, so in scan compression, what all the subtopics will be covered is in our course. So topic 2 is scan compression, or you can even call it as EDT insertion. Okay, so topic 2 is scan compression or EDT insertion. Both are same. Scan compression or EDT insertion. Okay, so in the first day of the scan compression training, you will be able to understand what is scan compression, and then what is the need of scan compression. What is the need of scan compression? So need of scan compression is nothing but the reduction in test time and reduction in test data volume, as we saw in the previous slide. Reduction in test time and reduction in test data volume. Reduction in test data volume. So test data volume is nothing but the number of bits of patterns. Okay, so that is what is called as test data volume, number of bits of patterns. So this, as I told, how we are able to achieve reduction in test time and reduction in test data volume if you go for scan compression. We will be explained both logically as well as with the help of formula. Logically also we will explain, and then we'll take the formula for test time and test data volume. We will substitute the values for values of the quantities which is present in those two formula, and then we will try to see, we will do a comparison with compression and without compression. We'll do a comparison, and you will be able to see how with the help of compression you are able to achieve reduction in test time and reduction in test data volume. And then you also have a quantity called as compression ratio. You also have a quantity called as compression ratio. So compression ratio is nothing but number of internal chains by number of external channels. Number of internal chains divided by number of external channels. So this is what is the compression ratio. Okay, compression ratio is number of internal chains divided by number of external channels. So we will try to understand about this compression ratio as well. And we will also try to understand how to decide the number of internal chains and number of external channels for a particular project. Okay, for a particular project, how to decide this number of internal chains and external channels. So that also we will try to understand it during the day 1 training. How to decide day 1 of the scan compression topic. Okay, how to decide the number of internal chains and external channels. Internal chains and external channels for a particular project. for a particular project. So how to decide it? That is what we'll be discussing it during this day 1 of scan compression training. All these things will be covered. And then from day 2, we will start with the we'll start to explore the architecture of EDT. So EDT logic, we will start to explore the architecture. Okay. So in day 2, we will understand about the decompressor component of our EDT logic. Decompressor component of our EDT logic we'll try to understand. And then on day 3, again we'll discuss about the EDT logic only. So the other components like compressor or compactor logic, and then those controller. These two things we'll try to understand it on day 3. And then on day 4, we'll try to understand about the EDT logic only. So like the bypass logic, and then like pipeline flops and compressor. Okay, pipeline flops and compressor, lockup cells in EDT. So all these things we'll try to understand it. And then on day 5, we'll try to understand. So like this compression ratio I told, right? Compression ratio is number of internal chains by number of external channels. So this compression ratio, we usually make sure that it doesn't exceed above 100x. And why it is like that? That is what we'll try to understand it on day 5. So we'll try to understand why we usually make sure compression ratio doesn't exceed 100x. Compression ratio doesn't exceed 100x. And some more extra points about this compression ratio, like merits and demerits of compression, high and low compression ratio, like that. Some more extra points about this compression ratio we'll try to explore. Merits and demerits of merits and demerits of high and low compression ratio. All those things we'll try to understand it. Okay. So these are all the topics which we will be covering when we do the scan compression part of the training. Okay. And next topic 3 is automatic test pattern generation, ATPG. So as its name suggests, it is a process of generating test patterns for a given fault model. There will be various fault models like StuckCAD, TDF, PDF, IDTQ, like that. So it's a process of generating test patterns for a given fault model. So during ATPG, what will happen? Test patterns will be generated. During ATPG, test patterns will be generated, and these test patterns will be used to test the chip after manufacturing. So after manufacturing, if suppose there are any defects, these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will be able to detect most of the manufacturing defects? It is because our tool does fault simulation to generate the test patterns. Okay, so during ATPG, test pattern will be generated. So these test patterns only will be used to test the chip after manufacturing. And these test patterns should be having a capability. What is the capability? After manufacturing, if suppose there are any defects, then these test patterns should have the capability to detect most of the manufacturing defects. And how are we sure that our test patterns will detect most of the manufacturing defects? It is because our tool does fault simulation to generate the test patterns. And ATPG, it is actually a very vast topic. Okay, ATPG is a very vast topic. It will take a long amount of time to complete this ATPG topic. Compared to the other topics, ATPG will take higher amount of time to complete. And ATPG also, it is not a very straightforward topic. So it will take time to complete. We'll just try to understand what are all the topics will be covered as a part of ATPG. So topic 3 is ATPG. So like I'm not writing day wise schedule because it depends. Okay, for each and every batch it depends based on how quickly you understand the concept. So as I told, like ATPG, those fault simulation, all those things are like not a very straightforward topic. So it differs from each batch. If you are able to, if you are able to understand it quickly, then we will be able to complete the topics little bit earlier. Otherwise, if it is taking time for you to understand, then it might take some more extra classes for us to complete the ATPG topic. So instead of writing day wise, I will just write out what are all the topics will be covered as a part of the ATPG training. Okay. So we'll try to understand what is ATPG, what is ATPG, and then we'll try to understand fault simulation. So this fault simulation is only it's not a straightforward topic. So it might take around 2 days to complete, two sessions to completely understand about this fault simulation topic. Okay, and then we'll be covering the fault models. We'll cover fault models. What is fault modeling also we'll try to understand, and what the various fault models we need to understand. So like we'll cover all these fault models like stuck cat fault model, transition delay fault model TDF, path delay fault model PDF, and then IDDQ fault model. So this transition delay fault model and path delay fault model, it is also called as UT speed test. It is also called as UT speed test. And then we will cover the various fault categories. We'll cover the various fault categories. Okay, so fault categories will cover what is called as fault dominance, fault dominance. Okay, what is called as fault equivalence, and what is called as fault collapse. We'll cover all these topics as a part of fault categories topic. Okay, and then we will try to understand fault aliasing. We will also try to see the internal architecture of on-chip clock controller OCC. On-chip clock controller OCC. And then we will try to understand about the fault classes. So fault classes means how the faults are classified. So faults, they are broadly classified as testable faults and untestable faults. So, and then each of them have their own subclasses. Like subclasses of this untestable faults are unused, unused, tied, blocked, redundant. Okay. And then for this testable class of faults, it is again subclassified as detected, possibly detected, ATPG untestable, and then undetected. Again, they have their own classification, subclasses, like detected means it will be having detected by simulation, detected by implication, and then ATPG untestable means it has its own subclasses like pin constraint, sequential depth, and then like cell constraint, wire, okay, mask primary output, etc. Okay, and then like yeah, so likewise, so each of them they have their own subclasses. So that is what the broad classification of faults, and then their subclasses, all these things will be covered as a part of the fault classes topic. And then we'll try to understand what is coverage, what is called as coverage, okay, and then like test coverage, what is test coverage, and what is fault coverage. Test coverage and fault coverage. Okay, and we will also understand about coverage analysis and improvement. Coverage analysis and coverage improvement. So during theory session, we'll try to see an overview about it. During the labs, we'll try to do this in detail. We will try to work on coverage analysis and coverage improvement. So during theory session, we'll see an overview. During the labs, we'll see that in detail. We'll also cover some more topics like dead cycles, pipeline scan enable, test point insertion. So these are all the topics which other topics which we will be covering it. So all these things will be covered as a part of ATPG training. So you will be able to understand it in detail when we do the videos. And then the next topic is simulations. So simulations means it is to validate the patterns which was generated during ATPG. So that is what is called a simulation. Okay. So simulation means it is to validate the patterns which was generated during ATPG. So before delivering the pattern generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that validation is what is called as simulations. Okay. So before delivering the patterns generated during ATPG to test the chip after manufacturing, we need to validate once whether proper patterns are generated or not. So that validation is called as simulations. Okay. So for simulations, we'll be covering both theory and labs will be done parallelly. Theory and labs will be done parallelly for simulation topics. Simulation topic will be done parallel. Okay, lab theory and labs will be handled parallelly for the simulation topic. So the concept of simulations, we will be covering it by practically demonstrating in the lab. So that's why theory and practical will be done parallelly for simulation topic. And then as a part of simulation training, these are all the subtopics which will be covered. So we'll first try to understand why do we need simulations? Why do we need simulations? Why do we need simulations? Okay. And then what exactly happens in simulations? what happens in simulations, what is simulations or what happens in simulations, what is parallel simulation, what is serial simulation. And yeah, in the ATPG, I forgot to tell one thing. We will also be covering pattern classification topic also. As a part of ATPG training, we'll also be covering pattern classification topic. So yeah, what is parallel simulation? What is serial simulation? We'll try to understand. Okay. So how to perform simulation using QuestaSim tool. So performing simulations using QuestaSim. And then like what are all the reasons for getting simulation mismatches, we'll try to understand. Reasons for getting simulation mismatches. Okay. And then how to debug the simulation mismatch. So simulation mismatch debug. How to debug the simulation mismatches. So all these topics will be covered as a part of the simulation game. And basically simulations, you will be having two types of simulations. So one will be the no timing simulations. One will be the no timing simulations. And the other one will be the timing simulations. So in our course, we will be covering only no timing simulations. Only no timing simulation is covered in our course. Timing simulation, it is not covered in our course. The reason is, in order to perform timing simulations, we require a file called as SDF file. And SDF file is not available for the test cases which is there in our institute. So that's why timing simulation is not covered in our syllabus. So currently timing simulation is not covered. So if in case you want exposure to timing simulations as well, you can once check with Srinivasa sir. So you can check with sir if it is possible for institute to provide training on timing simulations or not. Okay, you can once check that with sir. So currently, like in our DFT course, DFT regular course, no timing simulations is only covered. Timing simulation, it is not covered. In case you want exposure on timing simulations as well, then you can once check with Srinivasa sir if it is possible for the institute to provide the timing simulation training or not. Okay, so sir will check and let you know if it would be possible for the institute to provide the training on timing simulations or not. Okay, so this was regarding simulations. And then next is JTAG. JTAG is Joint Test Action Group. JTAG is Joint Test Action Group. So it's a IEEE 1149.1 standard. And why do we need to go for use JTAG? So we use JTAG DFT team. Okay, DFT team we use JTAG in order to minimize the number of ports from top level and also to achieve boundary scan. We'll try to understand this. So here if you see, I've kept a list of some important signals. So like this memory bypass enable, EDT bypass enable, int mode, ext mode, intel test enable, extend test enable, like that I've kept some signals, right? So these are a list of some important signals. There will be many more signals like these. Now, if all these signals are to be controlled from the top level, so which means you are allocating a top level port to control this memory bypass enable, one top level port to control EET bypass enable, one top level port for int mode, X mode, one for X mode, one for intel test enable, one for X test, L test enable. Like that, if you allocate a top level port in order to control each and every signal, then the number of ports from the top level it will increase drastically. Okay, so I've just kept a list of some important signals. There will be many more signals like these. Now if all these signals are to be controlled from the top level, that is if you allocate a top level port in order to control each and every signal, then the number of ports in the top level, the number of top level ports will increase drastically. So that's why we make use of JTAG in order to internally control those signals. Okay, so that's why we make use of JTAG to internally control those signals. So that is why we are able to minimize the number of ports from top level by making use of JTAG. Okay, you will be able to understand it when we do this course. So basically, during the JTAG part of the training, we'll first try to understand the JTAG tap architecture. Okay, JTAG tap architecture, and then we'll try to understand about the JTAG FSM. Okay, we'll also try to understand about the JTAG FSM. Okay, so when we try to understand about these things, when we try to understand about the JTAG architecture, the JTAG tap architecture and JTAG FSM, when we try to understand these things, simultaneously we will also explain how with the help of JTAG you are able to minimize the number of ports from top. Okay, so you'll be able to understand. And JTAG can also be used in order to achieve boundary scan. So what is boundary scan? First we'll try to understand. Okay. So chip 1, chip 2, chip 3, they are properly passing the test of DFT, but still the board is failing. What is it? We'll first try to understand. So first what will happen? Boundary scan. Boundary scan, it is actually, we go for boundary scan to test the interconnection between the chips. Okay, boundary scan is actually to test the interconnection between two chips. Test the interconnection between the two chips. Okay. So first what will happen is chips will be manufactured. First chips will be manufactured. Now after that what will happen is chips will be tested on the ATE. The full form of ATE is automatic test equipment. So that is what is the full form of ATE. We can also call it as a tester. Okay, so first chips is manufactured and then chips will be tested on ATE, automatic test equipment. Chips will be tested on ATE. Tested on ATE. ATE, we can also call it as a tester. So this is how you have. So this is what is the ATE, and this is how the chips will be tested parallelly on the ATE. So here in this case I have considered three chips like chip 1, this is chip 2 and then chip 3. Okay, so the input of the chip will be connected to the ATE and then output of the chip will be going back again to the ATE. Like this, input of the chip will be connected to the ATE, output of the chip will be going back again to the ATE. So now here in this case, what is happening? Chip 1, chip 2, chip 3, they have passed their test on ATE. They have passed their test on ATE. Okay, they have passed their test on ATE. So which means, as we saw in the initial slide, in the initial slides we have seen, right? Output of the chip will be equal to the expected output. That is what it means like passed the test on ATE. So output of the chip will be equal to the expected output. Will be equal to the expected output. So chip 1, chip 2, chip 3, they have passed their test on ATE. Output of the chip is equal to the expected output. It means that they are not having any manufacturing defects. Chip 1, chip 2, chip 3, they are not having any manufacturing defects. not having any manufacturing defects. Okay. And after this what will happen? Chips will be placed on the PCB board. After this, chips will be placed on the PCB board like this. Chips will be placed on PCB board. So this is the PCB board. And this is how it will be placed. So this is chip 1, chip 2, chip 3 like this, and then the interconnection between the chips and all are formed. Like this. The interconnection between the chips and all are actually formed. And after this what will happen? After this, board is tested. Board is tested. So when the board is tested, what is happening? It is actually failing. So why it is failing? Chip 1, chip 2, chip 3, they are internally not having any manufacturing defects because they have already passed their test on 80. So chip 1, chip 2, chip 3, they are not having any manufacturing defects. They are internally not having any manufacturing defects. Now why is the board failing? It can be due to the manufacturing defects in the interconnection between the chips. Okay, so this can be due to the manufacturing. So this can be due to the manufacturing defects. Manufacturing defects in the interconnection between the chips. Interconnection, interconnections between the chips. Okay, so this can be due to the manufacturing defects in the interconnections between the chip, between the two chips. And that's why we go for boundary scan. We go for boundary scan to test the interconnection between two chips. Okay. And during this boundary scan topic, what are all the things we will be covering? It is we will cover. So the topics which will be covered as a part of boundary scan courses, we will cover boundary scan cell structure. Okay, what is the structure of a boundary scan cell? Boundary scan cell structure. Okay, and then modes of operation of boundary scan cell. Modes of operation of boundary scan cell. And then like we will also be understanding some mandatory JTAG instructions. Mandatory JTAG instructions. Like sample preload, X test, okay, like sample preload, X test, and then bypass. Okay, and when we cover these topics in boundary scan, you will be able to understand how with the help of JTAG we are able to achieve boundary scan. Okay, here we have written right, another need of JTAG is to achieve boundary scan. So when we discuss these topics in boundary scan, you will be able to understand how with the help of JTAG you are able to achieve boundary scan. Okay, so these are all the things which will be covered as a part of our JTAG training. So first we'll try to understand about the JTAG TAP architecture and JTAG FSM. So when we try to understand this, we will also simultaneously explain how with the help of JTAG you are able to minimize the number of ports from the top level. and also to achieve boundary scan. So when we cover these topics in the boundary scan part of the training, you will be able to understand how with the help of JTAG you are able to achieve boundary scan. And then in our course, we will also be covering IEEE 1687 standard. So IEEE 1149.1 standard is JTAG. So in our course, we will also cover IEEE 1687 standard, which is nothing but IJTAG. We will also cover IEEE 1687 standard, which is IJTAG. Okay, so all these things will be covering it during the course. And then the last topic is MBIST, memory built-in self-test. So we use MBIST technique in order to test the memories. So what are all the topics which will be covered as a part of our MBIST training is? So we will cover the various memory fault models. We'll cover the various memory fault models. Okay, like stuck cat fault model, and then transition fault model, address decoder fault, coupling fault, like that. We'll try to understand. Okay. So during our MBIS part of the training, so first we'll try to understand the various memory fault models like stuck cat fault model, transition fault model, address decoder fault model, coupling fault model, all those things. And then memories. Memories, it will be tested using algorithms. Okay, memories will be tested using algorithms. So some basic algorithms we will try to understand. Okay, some basic algorithms we'll try to understand, like these things. Some basic algorithms like basic memory algorithms like 01 algorithm. Okay, 01 algorithm, and then checkerboard algorithm, and then maths, maths plus, and then maths plus plus, and then March X, March C. Okay, so these things will be coming under the March algorithms. Okay. So during this algorithm topic, what are all the things we'll be understanding is we'll be understanding the sequence of algorithm. Sequence of algorithm. Okay. So for each algorithm you have a sequence. So we'll try to understand the sequence of that algorithm. And then we will also try to understand which algorithm will be able to detect, will be able to cover which faults in memories and how. We'll also understand which which algorithm will be able to cover, will be able to cover which faults in memories, which faults in memories and how. Okay, so we'll try to understand this during the algorithm part of the training. And we will also try to understand descent invest. Descent invest. So descent invest means how to implement descent, how to implement invest using descent tools. Okay, implementing invest using descent tools. So that is what is called as descent invest. Okay. So like we will cover all these things as a part of test and tempest part of the training. So test and tempest implementation, and then test and tempest architecture. Okay, and then test and tempest operation protocol, operation protocol, and then grouping of memories, step concept. So these kind of things will be covered as a part of tempest training. Okay, so these are all the things which will be covered as a part of our theory course. And next, let us try to see about the lab part of the training. So before that, let me once check the chat box. Okay, so there are no messages. Yeah, then we can proceed. So in our labs, we will be covering IJ tag insertion, MBIST, scan insertion. So basically, there are two approaches in scan. One will be the top-down approach, and the other one will be the hierarchical scan approach. We will be covering both these approaches in our lab. And then we have the EDT and OCC insertion, ATPG pattern generation, ATPG and MBIS simulations. So these are all the topics which will be covered in our lab. And boundary scan, here we had seen, right? Boundary scan, this will be covered only theoretically. This boundary scan will be covered only theoretically. Okay, so this is covered only theoretically in our course. Okay, so like we do not have the license for boundary scan, so that's why it will be covered only theoretically. Okay, for labs these are all the things will be covered: IJ tag, MBIST, scan insertion. So scan insertion there will be two, like top down approach and bottom up approach. Will be covering both the approaches. And then EDT and OCC insertion, ATPG pattern generation, ATPG and MBIST simulation. So these are all the topics which will be covered in our labs. So basically our labs will be structured into four levels. So level 1, level 2, level 3, level 4. Like that the labs will be structured into four levels. So in level 1 projects you'll be having 11 test cases, case 1 to case 11. And these are like simple test cases. This level 1 and level 2 projects, these are like simple test cases. So simple test case means complexity will be less. Okay, so for level 1 and level 2 projects, these are simple test cases. Your complexity will be less. So you'll be having maximum of around 100 flops like that. Maximum of around 100 flops will be there. Maximum of around 100 flops will be there as a part of our level 1 and level 2 projects. Simple test cases. Okay, maximum of around 100 flops will be there. So in level 1 projects, we will be first performing the scan insertion for these 11 test cases. For those 11 test cases, we will be performing scan insertion. So among these 11 test cases, two test cases, two test cases will be to familiarize with the flow. Familiarize with the flow. So familiarize with the flow means if you are performing scan insertion using Tessin tool. Okay, if you want to perform scan insertion using Tessin tool, then you will be having some steps which you need to follow. Like what has to be done in the setup phase, what has to be done in the analysis phase, what has to be done in the insertion phase. Like that, there will be some steps. Okay, if you want to achieve scan insertion using metographic design means they will be having some steps which has to be followed in each phase, like scan setup phase, analysis phase, insertion phase. Like that, you'll be having various phases, what has to be done in each phase. So all those things, that is what is called as flows. So in order to familiarize yourself with the flow of scan insertion means in setup phase what you need to do, analysis phase what you have to do, insertion phase what you need to do, what are the various commands, how to open a schematic. So such kind of things in order to familiarize yourself with the flow, the commands as well as the tool environment, we'll be having two test cases. Okay, among these 11 test cases, two test cases will be basically for you to familiarize with the flow. Okay, to understand how to implement scan insertion using design tools. Okay, and then the commands, various commands, and then how to familiarize yourself with the tool environment, like how to open a schematic. Okay, so that kind of how to open a flop in a schematic, how to analyze the schematic, so such kind of basic things in order to understand, you will be first two test cases will be there. Okay, so to familiarize it with the flow and tool environment, let me write it, and tools. And then the remaining nine test cases, it will be for DRC debug. So as I told, if a flop has to be converted to a scan flop, then it has to pass certain rules. So those rules are only called as a design rules in DRCs. So you will be having some DRC violations. In the remaining nine cases, you will be having the DRC violations. Okay, and how to analyze that DRC violation and how to debug it, how to debug those DRC violations. So those things will be covered as a part of those things will be covered during the nine test cases. So each test case you will be having a different DRC violation. So how to analyze it and how to fix the DRC violation, that is what will be covered in this. That is what will be covered in the remaining nine test cases. Okay, and basically like these DRC debug, if you're using mentor graphics tool, it can be done using three ways to do the DRC debug. So there will be, you can manually edit the netlist and fix it, manual editing of netlist, or else you'll be having the auto fix method, or else you'll be having a method you can use these commands like create instance, delete connection, delete connection, create connection. Like this, you'll be having some set of commands like this: create instance, daily connection, create connection. Then you'll be having some set of commands with which you can actually fix the DRCs. So these are the three ways with which you can do the DRC debug, like manual editing of netlist, auto fix method, or you can use these three commands like create instance, delete connection, create connection. You can use these commands in order to debug the DRCs. We'll discuss about all these three methods with which you can debug the DRCs. So that is what will be the scan insertion part of the training, which is nothing but the level 1 projects. In level 2 projects, for the same 11 test cases, we will perform scan compression, which is nothing but EDT insertion, ATPG, and then simulations. All these things we'll try to do. Okay. So like in ATPG, we will be performing ATPG for all these fault models, like stuck cat fault model, transition delay fault model, and then IDDQ fault model. Okay, path delay fault model, it will be covered only theoretically. Practicals, it will be covered for stuck at fault model, transition delay fault model, and IDDQ fault model. Okay, so we will understand coverage analysis and coverage improvement. Okay, so like coverage analysis, coverage analysis plus improvement. Okay, test point insertion, how to practically do the test point insertion practicals, like using tickle scripts. You can insert the uh, test points using tickle script. Okay, or else you can, there is an automatic descent flow with which you can insert the test points, automatic descent flow with which you can insert the test points. So those kind of things. So coverage analysis plus improvement. So when we do the coverage analysis plus improvement, subtopic is test point insertion practicals. So we'll try to understand how to insert test points using tickle scripts, how to automate the process of test point insertion using tickle scripts, or there is actually an automatic flow in tessent with which you can insert the test point. So what is that flow? All those things we will try to understand it. Okay, so we will understand about pattern generation. So pattern generation like pattern generation with TDT, pattern bypass pattern generation, all those things we will try to understand. Okay, we'll also try to understand pattern generation with TDT. Okay, pattern generation with TDT, and then bypass patterns, all the bypass pattern generation, all those things we'll try to understand it. And then simulations. Simulation, as I told, theory and practical, we will be doing it simultaneously. Okay, so we'll be explaining the concept of simulation by practically demonstrating in the lab. So whatever I told at the time of simulation training, right? Simulation overview when I had given today. So the same topics will be covered here also. Theory plus practical will be done simultaneously. The theory concept will be explained by practically demonstrating in the lab. And as I told, we'll be covering only the no timing simulations in our course as of now. So if in case you want exposure to timing simulations, you can once check that with Srinivasa sir. So sir will let you know if it would be possible for the institute to provide the training on timing simulations also. Okay. And then EDT labs will be doing the EDT insertion. So like the EDT components, the decompressor, compressor, bypass logic, and then controller, all those logics and all will be there. Right? So the EDT logic has to be inserted into your design. So that is what we will be doing. How to insert that EDT logic into your design. So we will do that, and we will also try to like uh, view what logic has been, what is the EDT logic which you have added. We'll just try to view that in the schematic, and in that way we will try to correlate what we have learned in the theory and labs. So same way like we'll also analyze the output files which is generated during EDT run, and we'll also try to correlate what we have learned with the theory and what has happened in the lab. So those things we'll try to correlate it. So these are all the things which will be covered as a part of EDT training. Okay. And then like one more thing, in the part of ATPG training, I actually forgot to tell one more thing. We'll also be covering the tracing violations. Okay, tracing violations also will cover. I forgot to tell that. So as a part of ATPG training, we'll be covering the tracing violations also. Okay. And then level 3 and level 4 projects, these are higher complexity test cases. Okay, so this level 3 and level 4 projects only you can use it as a project work in your resume. This can be, you can write this level 3 and level 4 projects as a project work in your resume for this particular course. Okay, write it as a project work in your resume. Write it as a project work in your resume. So these are higher complexity designs. Okay, so for level 3 projects you'll be having around 4K flops. Level 4 projects you'll be having around 44K flops. Okay, so in level 3 and level 4 projects we'll be covering the entire flow like IJ tag and embist insertion. So in level 1 and level 2 projects and all, if you see, we have not done the IJ tag insertion, embist insertion, OCC insertion and all, it's not done, right? But in level 3 and level 4 projects we cover everything. So we will be covering the IJ tag and embist insertion, sorry, IJ tag and embist insertion, EDT OCC insertion, EDT OCC insertion, and then synthesis, okay, and then scan insertion, ATPG, simulations. Everything will be covered. The complete flow will be covered in the level 3 and level 4 projects. So level 3 projects is nothing but the hierarchical scan approach. And when we do the level 3 projects, at that time the concept of scan wrappers, then in test, x test, pattern retargeting, all those things you'll be able to understand. All these concepts also you'll be able to understand when you do the hierarchical scan. Okay, what are scan trappers, what is in test, x test, what is pattern retargeting. So such kind of things you'll be able to understand when we do the hierarchical scan topic. And level 4 projects is nothing but the top down scan approach. Okay? And in level 3 and level 4 project, the complete flow will be covered like IJ tag, MBIST insertion, EDTOSIS insertion, synthesis, scan, ATPG simulations, everything will be covered. Okay. And then, what are the tools used for DFT? So these are all the tools which is available in the market. So in our institute, we'll be making use of the metagraphics tools. For Okay, we'll be making use of the meta graphics tools. For MBIST, we'll be making use of Tessent MBIST. For scan, we'll be making use of the Tessent scan. For scan compression, we'll be making use of Tessent test compress. For ATPG also, we'll be making use of Tessent test compress. And then simulations will be making use of Quest. Okay. MBIST will be making use of test and MBIST, scan, test and scan compression, test and test compress, ATPG test and test compress, and then simulations, quest asset. All these things will be covered. These are the tools which we will be using in our course. So mental graphics tools will be using. At one point, we need to run the synthesis. So that alone will be making use of the synopsis tool. For the synthesis alone, we will make use of the synopsis tool, which is nothing but the design compiler. Okay. At one point we need to run synthesis, so for that alone we'll make use of the synopsis tool, which is the design compiler. For all the other things we'll be making use of the meta graphics tools. and and who can all attend this course? So a student from final semester who is seeking DFT as their course curriculum, okay, you can attend this course. Okay. Or also new college graduate who is from relevant branches of engineering and science. Okay. And then lecturers and professors who want to switch their career into real-time industry experience. And then we want working professionals with similar or other VLSI domains. So say for example you are there in physical design team. Now you want to switch to DFT. Then you can attend this course. Okay, or else if you are there in IT sector, if you want to move to VLSI, you can also attend this course. Okay. And placement support. So we are having tie-up with various VLSI companies. Students are entitled to placement support based on their performance in the course assignment. So so during the course, like you'll be given various assignments and then presentation sessions, tests, mock interviews. All those things will be covered. All those things will be conducted. So based on your performance on all those things, you will be given an opportunity to attend the placements. Okay. And then mock interviews will also be conducted so that you will gain a confidence while you are facing the original interviews. Okay, mock interviews will be covered so that you will gain a confidence for attending the interviews, for attending the main interviews. So previous company interview questions and preparations. Okay, so previous company, like previous batch students, they would have attended some companies, right? So they would have faced some interview questions. So what are all the questions which was asked for them? Okay, and a training will be given for those things as well. Okay, like if any application oriented question is asked, okay, which is not directly covered in the course, so such kind of application oriented question training also will be given. Okay, so for each topic, like I have prepared application oriented interview questions which was asked in the previous batches, so we will be training you with that as well. Okay, so like DFT interview, so difficult interview questions with answers. So we'll be like covering what are all the difficult interview questions which was asked in the previous company interviews, and along with answers we will train it. Okay, we'll be training you along with answers like this. Okay, so some points, some application oriented questions, or else some questions which is actually not directly covered in the course, if it was asked in the previous company's interviews, then in those kind of situations, so these those kind of questions also we will be providing the training. Like say for example, um, during our course you will be able to, we will see that scan insertion will be performed on a gate level netlist. Okay, just for an example I'm telling. So during our course when we do the lab session we will see that scan insertion will be performed on a gate level netlist. So in one of the question, in one of the interviews, the interviewer had asked why scan insertion is performed on a gate level netlist, why it is like that. So how to answer those kind of questions? So these are all the application oriented questions. So how to answer those questions? So we will train you on that as well. And we'll also give you like the question bank as well as like easy questions, previous company easy questions. So these kind of questions would have been directly discussed in the course, like what is scan insertion, what's the difference between DFT team and verification team. These kind of questions will be directly discussed in the course itself. So these kind of questions also, what was asked in the previous company. So those kind of questions also we will give it to you. Okay, easy questions, direct interview questions which was asked in the previous company. So those list also we will give you. We will also train you with the application oriented questions. So what are all the application oriented questions which was asked in the previous batches? We will train you with the answers as well. Okay. So yeah, so and then question banks, all those things also we will provide it. So this is how we will be like giving you the placement support, like we'll be training you for the placement and you will also be given opportunities to attend the placements. Okay. And yeah, and before that, like one more thing which I want to tell is this course, so this complete DFT course, it will be like two parts. So first few months basic training will happen. First few months basic training will happen. So it might go around for 2 months. Basic training might be for 2 months. Okay, so I'm not exactly sure about the basic duration. So I think it will be for 2 months. So during the basic part of training, we will be covering digital design. Okay, digital design, and then Linux. Okay, Linux, Tickle. Okay, Tickle, GVim, basics of Verilog, basics of Verilog. Okay, and then CMOS. So all these topics will be covered during the basic training. So an basic understanding of these things is required in order to take up the DFT advanced training. Okay, so that's why in the first 2 months all these things will be covered. So like so that you'll be able to. So these concepts are required in order to start the original DFT course. So that's why in the first 2 months this DFT basics training will happen. And after that only the advanced course starts. After completing this the DFT advanced course will start. Okay, so in the DFT advanced course it will be like it was a 3.5 months to 4 months course. 3.5 months to 4 months. So it depends. So some batches we can complete it within 3.5 months. Some batches it might take around 4 months. So as I told, those ATPG and all, it is not a straightforward topic. So some batches will be able to understand it quickly. In some batch it might take some time to understand. So that's why it depends on the batch. It depends on how quickly you understand the things. Okay. So that is why this DFT advanced course will be from 3.5 months to 4 months. So some batches will be for 3.5 months, some batches will be for 4 months, like that. It depends on how quickly you understand the points. Okay. So whatever I had told, whatever course outline and lab, whatever I told will be covered. Okay. So whatever course outline and labs, theory course outline, theory plus lab course outline, theory plus lab course outline, whatever I presented in the previous slides. Whatever I have presented in the previous slides will be covered. Okay, during this training, whatever theory plus lab course outline I had presented in the previous slides, right? So those topics will be covered as a part of this DFT advanced course. And then I will also cover basics of static timing analysis. Basics of static timing analysis. So static timing analysis is STA. So static timing analysis, STA. So like it's not a DFT part, but some companies expect you to know some basics of STA as well. So we'll also cover basics of static time analysis. So like some what is STA, what is setup time, what is hold time, setup violation, hold violation, and their fixes. Why, which one is more critical, whether setup time is more critical or hold time is more critical, why, and then like some problem questions related to like some numerical questions related to that STA. So what all the things will be asked in the interviews for DFT interview, what all the things will be asked, okay, what kind of questions will be asked. So such kind of training we'll also give for the static timing analysis. So these are all the things which will be covered as a part of our course. Okay. Yeah. And like once you enroll into the course, you will be like added into a group called as added into an individual group with your VLSI guru ID and your name. Okay, there will be a group with your VLSI guru ID and name. So if you have any doubts regarding how the sessions will be conducted for you, whether it will be a weekdays training or weekend training, and then duration, like session, each session, how much duration it will be there, okay, and then whether it will be online or offline, or any queries related to placements, or else anything related to fees, or any other technical doubts, whatever you have, you can just post it in that individual group. Okay, anything related to the course, anything, whether it is like related to session, or else like technical doubt, or else related to placements, any queries regarding placements or any queries regarding fees, if you have anything, you can post it in that group. So like respective faculty will address the queries. Okay, so do you have any questions? Yes, lab sessions will be conducted parallelly along with theory classes. Okay. So usually like how the uh, uh, sessions will usually be there is during the weekends. Okay, so during the weekends, okay, most of the batches, this is how the schedule would be there. So during weekends, okay, theory session will be conducted. Okay, so this is both for weekend only students, weekend only students as well as students who have enrolled for full week training, for both. Okay, during the weekends, theory session will be conducted. So both for weekend only students as well as the students who have enrolled for full week training. Okay, so this will be common theory class. And then theory session will be happening in the morning, means afternoon lab session would be there. So this lab session will be for weekend only students. This lab session will be for weekend only students. And then during the weekdays, lab session will be there, but this lab session will be for the full week training students. Okay, so this is how for most of the batches it would be there, and this is for the DFT advanced course. This is for the DFT advanced course. Basics how it will be conducted, I'm not sure. So you can like message in that. Like once an individual group is created, right? You can message them. So they will let you know how the basic training will be conducted for weekend students. So that I'm not very sure. Basic training how it will happen for weekend students. Okay. So once an individual group is created, right? You can just check in that individual group how the basic part of the training will happen for weekend only students. Okay, so DFT advanced course, what will happen is during the weekends, common theory session will be conducted for both weekend only students as well as the students who have enrolled for full week training. In the morning theory session is there, means afternoon lab session will be there, but that lab session will be only for weekend only students. And then during weekdays again lab session will be conducted, and that lab session will be for full week training students. Okay, so this is how most of the times, most of the batches, this is how the sessions will be conducted for DFT advanced course. Simulation like Questasim we will be using. We will be making use of Questasim tool, which is starting with the meta graphics tool. How to get added into the individual group? Like once you enroll into the course, like they will be adding you into a group. So with your VLSI Guru ID and your name will be there. So in that group you can actually message. Or else like I will share with you the contacts. You can like check with them as well. One second, I just share with you the contacts. Just a second. uh, e-learning students are like for e-learning students, like you'll be given pre-recorded videos. Okay, so pre-recorded videos would be given, so you need to go through the pre-recording videos as per your pace. You can go through it, and then like if you have any questions you can post it in that individual group, or else if you require any support sessions, that also you can post it in the individual group. So support sessions will be conducted separately for the e-learning students. Okay, so pre-recorded videos will be given, like previous batch training videos and all will be there, eh? So those training videos will be given, pre-recorded videos will be there. You need to go through the pre-recorded videos at your own pace. You can go through it if you have enrolled for e-learning course. Okay, and then like what is it, if you have any questions you can post it in that group, individual group, or else you can like request for a separate support session also. Okay. Yes, notes and materials, it will be available both for weekday students and weekend students. So like this, we will create a Google Drive and we'll be uploading all the notes there. So like this, we will create a Google Drive and then all the session notes will be uploaded there. So it is common for both weekdays and weekend students. It will be uploaded. The session notes will be uploaded like this. And some notes and materials, you can also find it in the InSkill portal. Okay, so some notes and materials will be available in the InSkill portal as well. Separately for the that session notes if you want, so that will be uploaded in this Google Drive like this. And what is, how many months tool access will be there? Okay, one second, I will just share with you the number. So regarding like tool access, you can contact Usha ma'am. So I'll share with you her number. Okay, just a second. And can e-learning students attend weekend labs? Yes, I think you can once confirm that as well. Just a second, I will like message the contacts. One second, you can once contact them and see. Uh, so this is Usha ma'am's number. One second, I'll just type it and share it in the chat box. So this is Usha ma'am's number. You can once check with her regarding tool access and who can attend the course. There is a query there, right, whether e-learning students can, whether e-learning students will be able to attend the weekend lab. So there was a question over there. So though I think you can attend it. Okay, e-learning students will be able to attend the weekend labs, I think. You can once confirm it with Usha ma'am. So this is her number. So regarding tool access, how many months tool access will be there? Okay, how many months tool access, tool validity? Okay, tool access validity and who can attend this course, all those things you can once check with Usha ma'am. I'll give you her contact. Okay, so you can check with her. Lab instructor will be available in the labs. Yes, lab instructor will be there in the labs. Okay, and then mm, what else? Or else generally if you want anything like regarding placement, and Usha ma'am, you can even contact for fees queries, fees related queries also. Um, queries also, you can contact Usha. Okay, I've shared a number on top, and then I just share Vaibhav sir's number as well. So like you can check with sir. Like if generally if anything you want to ask, you can check with sir. So this is Vaibhav sir's number. So anything related to placement, or any general queries if you want to ask, you can ask sir. Any general queries. Okay, you can check with Vaibhav sir. I've shared his number. So any queries related to like batch timings, all those things, you can check with Manohar sir. So batch timings, and then like schedule. Okay, you can check with Manohar sir. So I'll share with you his number. Okay. So anything regarding batch timings and schedule, you can check with this sir. I've shared the numbers. You can any queries if you have, you can contact them, and you can see. Or else if an individual group is there, so if you are, once you get enrolled into the course, they will be adding you into an individual group with your VLSI Guru ID and your name, so you can directly post the message in that group as well. Yes, so like what will happen is you'll be like tools will be loaded onto the institute server, so you'll be given a VPN access like this. So you'll be given a VPN access, so you can connect to the institute server. So in your personal laptop, you'll be like you'll be given the VPN access, so through which you can connect to the institute server like this. Okay, and then like so, and then you can access the tools from your personal laptop like this. Like this, if you want to invoke the testing tools, you can invoke it. You can access the tools like this. Okay, like this, you can access the tool. So tools will be available in the institute server. So like using VPN access, you can like connect to the institute server and you can use the tools from your personal laptop. Okay, like this. Okay. Any other questions which you have? Yes, simulation and debugging will be covering. So like simulation and simulation mismatch debug we will cover. Okay, but that will be only for no timing simulations. Okay, so in our course we'll be covering only the no timing simulations. So simulation mismatch and how to debug the simulation mismatches. So will be covered, but that will be only for no timing simulations. So if you want exposure to timing simulations as well, then you can once check with Srinivasa sir. Sir will let you know if it would be possible for the institute to provide training on timing simulations also. Okay, but currently in our course only no timing simulations will be covered. Yes, basics also will be recorded, advanced session also will be recorded. Then if there are no more queries, then we can end the session. If you have any queries, you can just contact them. So I've messaged their numbers in the chat box. So you can just make a note of their numbers and then you can contact them if you have any further queries. Okay, yeah. Thank you all. We'll end today's class. Yes, Jagan, you can ask. Yes, embedded insertion it is performed in RTL in our case, in our course. Embedded insertion on RTL. That is what will be covered in our course. Okay, so we'll be doing the embedded insertion. We'll be doing this IJ tag and embedded insertion on RTL. EDT and OCC insertion also will be performed on RTL. Then we will be synthesizing it. After that, we'll be doing the scan insertion, ATPG and simulation. So in our course, embedded insertion RTL is only covered. Yes, electronics and instrumentation, E and I, you can enroll for this course. Then, yeah, thank you all. We will end today's class.